Hello and welcome to the session where we're describing the boundary conditions which are used together with our differential equations to develop a particular solution. So we've been deriving the mass balances that can, when integrated, describe the concentration as it varies across the space. And in one of the previous case studies, we showed that our differential equation can look something like this. So this differential equation is describing that the rate of change of our concentration is equal to the gradients, or it arises from gradients in two directions, and these two terms are about gradients in the z direction, in the axial direction, and that's due to diffusion axially and convection axially, and then we also had diffusion radially. So this equation is a fifth order equation. So here you have as many as three independent variables, t, z, and r, and it's first order in t and second order in z and second order in r. So we count this as 1 plus 2 plus 2 is 5. So we need as many as 5 boundary conditions to solve a particular to get a particular concentration profile in this space. And we acknowledge here that our concentration varies as much as this, right? Our concentration is a function in t, z, and r. So we need to solve for a profile like this. So the only way we can do that is with boundary conditions. So let's review now some of the main boundary conditions that occur. And just before we get into the time one, so we'll be looking at the time one first. So before we do that, we just review that if we have some ordinary differential equation, doesn't have to be first order ODE only. If you have any differential equation, then if you have an initial condition, that means if you know the value of y at some value of x, then you can solve that equation. So you can use this piece of information. That means you know the value of y at one value of x, and then you can stick that value of y in here and estimate the gradient, and then step forward to the new value of y, and you repeat that process and span out a solution. So if you have an ordinary differential equation, an equation in just one independent variable, and there's just one output here, then we just nail down one condition, and then that spans out a solution for us. Now, by analogy, in our situation, we have time. So let's say we're talking about time first, and we're thinking about an initial condition. That means initially in our system, we have a value for the function at some value of t. So by analogy with this previous case, we know that if we know the value of the function at one instant in time, we can step that forward using the gradient, and we can span out a solution. However, in this case, our variable is not a scalar anymore. Our variable is a function that's also varying in x. Well, we can think then about partitioning this function in x into a series of values, and it's simply the case that we know the value of that function at multiple values in x. So we can say we've got some space in x here. So we've got some series of values in x, and we have some function. So our concentration might be varying like this with respect to x. So that means we have, at some instant in time, we know this function. Well, I should write this here. So for some time t equals 0, we know this function. And so we could specify specific parts of this. We could pick points on this curve and say, well, if we know the function at this t equals 0, we could step each of these points with respect to x forward in time. So we choose a value here that tells us the concentration at t equals 0. We step it forward, we get a new value, and we can do that for each of these. So we might step this function forward in time, and that might give us the value of the function at the next instant in time whatever it is. Right, so this is at t equals t1. So the point here is we know the value of the function, even though in this case it's varying in some other variable, we still know that whole function at a specific instant. So we have this function at some instant in time, and so that's our initial condition. Right, so this is the known function. So that's the so-called initial condition. And you see that would be quite enough to satisfy at least this requirement. Here it's first order in t, so we need one equation. And so we just specify that we need to know the whole function at some instant in time. So that's initial condition. And then under spatial boundary conditions, we are now talking more about the types of conditions for the z variable. So let's look at the z variable. And the first thing we could imagine is that we simply know the inlet conditions. And I believe I have a diagram here, yeah. So if you have a pipeline and fluid is flowing along this pipeline, then you could simply know the concentration of the feed stream, and you could make the jump and say that, well, the concentration in the feed stream must be the same as the concentration immediately inside this tube. And so you could claim simply to know the inlet concentration. And so you can say now at x equals 0, we know the concentration. And this is true for all time. So in contrast to the earlier case where we were talking specifically about a specific time, which we called an initial state, now we are talking about all future times. Looking just at the inlet point, we happen to know what the concentration is at that inlet point. And we accept that this might be changing with time. So back to our picture, if we were changing the concentration at the inlet, then that would simply change the inlet condition here. So we are not concerned that with this being constant or anything like that, that might be changing with time, but that doesn't invalidate this condition. We can still say that the concentration at x equals 0 equals that value. Right, so that's a boundary condition we can apply at the inlet point. At the exit point, it's a little more complicated. So at the exit point, a number of things could be going on. Number one, we could simply know the concentration at this exit point. However, that's probably that's fairly unlikely situation. Most of the time, the whole reason for developing the mass balance is because we don't know the concentration at this exit point. So quite often it is not known here, and it would be very nice if we did know it. It would be quite easy to solve the mass balance if we knew it, but quite often we don't know it. But we list it as a possibility. So depending on the information given with the question, if we had happened to be given the exit concentration, we could use this condition. So we would simply specify that at the exit point, which we specify as the spatial variable equals the end point, that's a known time function. So this is valid for all time again. Right. Another possibility instead of this is, so if we don't have this information, right, so I'm not saying now that all these are equivalent, that all these apply. It's any one of these could be considered. So the second possibility is that we don't know the exit point, but if we think about it, if we consider the time range that we are interested in, and that's one of the specifics of the problem. You would ask, how is the concentration varying in the space over a certain time range? That's one possibility. We can say, I want to know how the concentration is changing across this tube after 1 hour. Or you could say, I want to know what it is at steady state. So now let's say we are not talking about steady state. Let's say we've specified a certain time range. Then if we go and consider the diffusivity and the flow rate and things like that, we might conclude that not enough time will have passed to influence the end point. We could say the pipeline is long enough that I know that the end value will not have been influenced as yet. So in that special case, we can claim that the concentration at the end point over the time range of interest is still the initial concentration. So this is another possibility. And again, this one is not something that we would default to. So this is rather a special case, and it requires us to do a bit more work in terms of some calculations to determine whether enough time has passed and whether we really are interested in only a specific time range. So this one is also a little restrictive. Another possibility, so again, this one would replace any of the other two. Another possibility is that your pipeline might be long enough that by the time you reach the end, you can claim that the gradient is zero there. So you could claim that all the action is happening early on in the pipeline. And maybe let's just sketch that again. So, and in fact, it's similar here. So if you have a long enough pipeline, you can say all the changes are happening here. By the time you reach the end, everything has died out, and the gradient is fairly flat there. So if that's the case, then you can claim that the gradient at the end point is zero. So this condition is used fairly widely. So sometimes it's called rather commonly the long pipe assumption. So the pipe is long enough that the gradients have died out by the end point. And with all these, please note, we are always being very specific that we are referring to the end point, right? So you always, you never want to write this without the specific, the location specified there. Okay, so that's one possibility. But all these, as I say, are quite speculative, and there are some things you can do to support your speculation. You can look at the flow rates and the diffusivities and say, well, given these numbers, I can support one of these. But the most secure one, according to me at least, the one that I prefer is this one, where we simply state that at the exit point there's continuity. So we say that the gradient just inside the tube equals the gradient just outside the tube. So there's no change in the gradient. That doesn't mean the gradient is zero, right? dc dx just inside and just outside, that's not zero. It's generally some constant, but it is constant in x. It's not changing when you just exit the pipeline. So if it's constant, then of course you could subtract on this side and divide by delta, and so you can say that that's the same as saying d2ca dx squared at x equals L equals 0. So I use this one the most, and it gives me the best results, and I don't have to say specific things that I'm suspicious are actually going to let me down later on. So I like this condition, and you can see already in some of the early examples where I've implemented this. So anyway, these are all about the z direction. So coming back to the picture, we've talked about time, we've talked about z, and now we've got left over r, right? If you look back at our original equation, we've talked about needing one initial condition for t, and then for z we need two. So we have one possibility for the inlet, which is that we simply know the inlet concentration, and then we have the other possibility, which is that we have some condition for the exit as well. So we had four possibilities on the exit side. So now let's switch over to a different kind of boundary condition, and here we are looking at the final spatial dimension here, which is the radial position. And coming back to the picture, we can see here that we have two radial positions where boundaries might arise. The obvious one is the outer surface here, where lowercase r equals uppercase r. That's just how we define the radius there. And then we can also think about at the center line position, where r equals 0. And we can think about the condition of symmetry here. So if we imagine that the tube here is immersed in some fluid, and that fluid is attacking the pipeline here from all directions. So like in the previous case study where we had possibly a permeable wall, then we have the same concentration on the outer rim of the wall. That means we have the same diffusion rate from all directions in towards the center. So if you look at the center position, you can imagine that the concentrations are coming, the concentration looks the same in all directions. That implies to us then that the concentration is flat at the center position. And we can imagine multiple radial, so we can draw any number of radial lines through there. And if you pick, for example, a radial line like so, then you can imagine the concentration here will be the same as the concentration there. And so we can say that at the center position, there's no difference in the concentration. And so the gradient in the r direction with respect to concentration is 0. So that's simply a consequence of symmetry. And in fact, this symmetry condition can arise in other geometries as well. It doesn't have to all be cylindrical. So it could happen in spherical coordinates. So instead of disks like this, if this was just a ball, so if it was a sphere and we had we had flux into that sphere from all directions, then again at the center we would have a flat gradient. We would have the same concentration at the center. Even if we have rectangular geometry, so let's say we have a slab like this. So if we have the slab that's immersed in some kind of fluid, and we've got the same concentrations on both sides, we can easily imagine that a concentration gradient may develop like this. So there is some non-zero flux that's going on, but near the center, it's looking the same in both directions. So in this case, we would write this as dc dx equals 0. So at the point of symmetry, we can say we expect a flat gradient. So that's yet another possibility. Okay, then we've discussed this in some detail in the previous section on film theory. So we established that we could connect the concentrations in different phases. Number one, using the equilibrium relationship. So, for example, if you are just on one side of an interface, you could relate the concentration on that side in that phase to the concentration in the other phase across the equilibrium constant. So you could use the equilibrium constant, use the concentration in the other phase, and then you would estimate the concentration on the other phase. And so here we accept that this is going to hold for all time. Right, whatever else is going on in this phase, it's being dominated at this point at least by this equilibrium. So there might be other things going on in this phase that cause the concentrations in that phase to change, but all of those other processes can't really compete with what's happening immediately with the neighbor to this phase. So it's likely that this condition is going to hold for all time. And of course, we've discussed the mass transfer films in some depth. So we said that typically, across the equilibrium jump, that there's a variation in concentration, and that we could estimate the flux in terms of the gradient there. And then we could write the mass transfer flux in terms of the mass transfer coefficient. And then we could convert that into a flux which was equal to the diffusion gradient. So the diffusion gradient multiplied with the diffusivity, that's equal to the mass transfer rate. All right, so we have all the possible boundary conditions that can occur in problems of this nature. And so we hopefully have the confidence now that when we are presented with our partial differential equation, when we've done our material balancing and we've determined how the differences in each variable is related to the differences in the other variables, that we are then able to specify enough conditions around that situation and then go on to solve that. So of course, once you have this equation and you have enough boundary conditions, you can then determine a kind of numerical scheme which can be used to get actual numbers out and show us how the concentration is varying in time and Z and R and all those good things. Before we go on to numerical solutions, however, we want to think about trying to generalize these equations, because this arrived with some pain to us, right? And we had to apply quite a lot of rigor to eventually obtain these equations. And further to that, we can imagine that we will have to redo all this each time we change the geometry. So this is the equation that applies in the case of a cylindrical object, but we could imagine that we might have a rectangular conduit instead at some point in the future, or some other shape. And we then realized that in principle we would have to rederive all these equations. So there's a concern to us about the range of applicability of what we've derived, but we are also we are also suspecting that there might be some methods available in something like maths to help us generalize that. So in the next section, we're going to look at generalizing our equations to other geometries and even to other types of balances.